Hello everyone, today we're going to be talking about spanning trees, and let's start off with the basic definition. A spanning tree is a subgraph of your graph that is a tree and hits every vertex. All right. So, okay. So it's a subgraph, meaning it's made up of some collection of edges that are already in your original graph, right? You have to use edges that are only in the original graph. You can't add on new edges when you make a spanning tree. That's not what we're talking about. Okay. So for instance, in this example, we're restricted only to these edges that are already in the graph. We have to pick from those. And for it to be a spanning tree, we want to pick from those. We want to touch every single vertex, and we want to have it be a tree. So let's discuss for these three spanning trees that we've drawn, these three subgraphs rather that we've drawn, which ones are spanning trees. So first let's check out this green graph. Well, it's a subgraph because it's only edges that exist in the original, and it's a tree. There are no circuits in green, but it fails to hit every vertex. So this is not a spanning tree because it misses two vertices. And let's go ahead and look at this one in pink. So again, spanning or subgraph means we've used only edges that were in the original one. We haven't added any new ones. That's not allowed. And let's check this out. So we hit every vertex. So it's spanning, but we have a circuit here. So again, this fails because there's a circuit. So it's not a tree. Okay. And now let's look at this last one in blue. So we see we hit every vertex. We use only edges that were in the original graph and not any new ones. And there aren't any circuits. So when we look at the edges that we're using, there's no circuits. So this is yes. It is spanning, it hits every vertex, and it's a tree. Okay, let's move on to our next topic, which is redundancy. All right, here we're going to let E represent the number of edges in a graph, V represents the number of vertices, and R represents the redundancy. So there's a couple different ways we might see this formula. One way is the number of edges minus the quantity of the number of vertices minus 1. So another equivalent way we could write this, we could just take that negative sign and distribute it. So we could do edges minus vertices, and then negative times negative makes a positive. So edges minus vertices plus 1. And let's go ahead and compute the redundancy in this graph below. It's a K5, incidentally. It's a complete graph on 5 vertices. So let's first, number of vertices is 1, 2, 3, 4, 5. Number of edges, well, let's count them. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so the redundancy is going to be number of edges minus number of vertices plus 1. So in our case, number of edges is 10, number of vertices is 5 plus 1. So 10 minus 5 is 5 plus 1, which is 6. Okay, and let's talk for a second about what redundancy means. So redundancy is essentially the number of edges beyond what you need for a spanning tree. So for instance, in this complete graph down below, well, let's pick a spanning tree. So we could use this one, we could use this edge, we could use this edge, and we need to hit this vertex down in the bottom right still, and there's any number of edges we could use. Let's use this one. And let's remember what matters here is only the vertices, right? This crossing is just how we've drawn the graph. We don't create a vertex there, so there's not a circuit. This is a fair spanning tree. And we'll notice there's 1, 2, 3, 4 edges in the spanning tree. So a spanning tree has 4 edges. So that 4 plus the redundancy is what gives us the total number of edges. So we only need 4 edges for a spanning tree. Our graph has 10. That difference is the redundancy, which is 6. Okay. And let's go ahead and talk about one last concept here, which has to do with weighted graphs. We'll see more about this in the next couple of sections. So an MST, or a minimal spanning tree, is a spanning tree with the lowest total weight, and a max ST, or maximal spanning tree, has the highest total weight. So what we're looking for here is spanning trees where we look at the total weight of those edges and see what's highest and what's lowest. Well, here we have a really simple weighted graph, the same one drawn twice. And let's think about a spanning tree is just going to be any 2 of these edges. And if we're looking for an MST, a minimal one, well, let's just pick the ones with the lowest weights. So 5 and 10 is 15. Any other pair we choose is going to be higher. So there's a minimal spanning tree. And let's find a max ST in this one. And in an example this simple, we can just say, well, pick the one with the highest weights, 10 and 15. So the total weight here is 15, and the total weight on the max ST is 25. And we'll talk more about that in our next section. That is all for today.